In this lecture, we'll review asymptotic notation. We'll discuss big O notation, big omega notation, big beta notation, hierarchies of functions, and properties of asymptotic notation. First, we want to discuss why we bother with asymptotic notation. Asymptotic notation helps us compare the growth rate of functions. Sometimes we only care about what happens as the function grows very large, the input to the function grows very large. In computer science, this is important when we consider the scalability of algorithms. We want to know how many resources we need in terms of time and space for this algorithm as our input grows. First, we consider big O notation. Big O notation is analogous to less than or equal to for functions. More formally, we say that a function f of n is a member of the set of big O of g of n if there exist positive constants c and n naught such that for any n greater than or equal to n naught, f of n is less than or equal to c times g of n. That means that f of n is bounded above by a constant times g of n. You'll notice that we're dealing with non-negative functions when we're discussing asymptotic notation. So in this figure, f of n is the log of n, and g of n is n squared. And it's important to note that n naught is like a threshold, so the functions can be doing whatever they want before n naught. But after n naught, and as n goes to infinity, f of n has to be bounded above by c times g of n. We can also define big O notation in terms of a limit rule. We say that f of n is in big O of g of n if and only if the limit of the ratio of f of n divided by g of n as n goes to infinity is finite. This means it can be 0 or a constant. Let's try a practice problem now. This practice problem is 2 raised to the n plus 1 in big O of 2 to the n. There's several ways we can do this. We can apply the limit rules, or we can apply the formal definition. We'll try both now. So applying the limit rule, we need to take the limit as n goes to infinity of 2 to the n plus 1 over 2 to the n. And when we do that, we just get 2. That's a constant, so we can write that 2 to the n plus 1 is in big O of 2 to the n. In order to apply the formal definition, we need to find our constants. So we need to choose our n naught and our c greater than 0 such that the definition holds. For example, if we let n naught equal 10 and our constant equal 5, we know that for all n greater than or equal to 10, 2 to the n plus 1 is going to be less than or equal to 5 times 2 to the n. So the definition holds. Now, it's important to observe that we have many choices for n naught and for c. And with big O notation, we need only find one n naught and one c such that the definition holds. Now, let's consider if 2 raised to the 2n is in big O of 2 to the n. First, let's apply the limit rule. So we're going to take the limit as n goes to infinity of 2 to the 2n divided by 2 to the n. When we do this, we get the limit as n goes to infinity of 2 to the n, which is infinite. So 2 to the 2n is not in big O of 2 to the n. Another way we can do this is by using the formal definition and essentially a proof by contradiction. We'll come back to proof by contradiction, but I'll do this example now. Let's assume that 2 to the 2n is in big O of 2 to the n. If that's the case, then by the formal definition, there exist constants n naught and c greater than 0 such that for all n greater than n naught, greater than or equal to n naught, 2 to the 2n is bounded above by this constant times 2 to the n. Okay, but let's consider if this is possible or not. So now, let's just divide both sides by 2 to the n. This means that when we divide that equality by 2 to the n, we get that our constant has to be greater than 2 to the n for all n greater than or equal to n naught. Our intuition is already suggesting that this is not possible. That wouldn't really be a proof. That's just our intuition. So now let's choose a specific value for n and show that this can't possibly be the case. So let n hat be the maximum of c, our constant, and n naught. And let's see what happens to that inequality. So this inequality is supposed to be true. I'm going to highlight it now. This inequality has to be true, but now we're going to plug in n naught for the value. So when we do that, we're going to get 2 to the n hat has to be less than or equal to c, but we see that n hat has to be either c or n naught. In either case, it has to be at least as big as c, and now we're taking it and raising it to the power. So we're taking 2 to the c. It has to be at least 2 to the c, so then it's certainly bigger than c. So that is our contradiction, and 2 to the 2n is not in O of 2 to the n. So